We were talking about metric spaces last time, but actually we've said all that we want to say about metric spaces. There's sort of two main big topics left for the semester, and they are two types of sort of spaces or sets. I've heard that a typical course in topology is mostly about the 3 C's, and they are continuity, connectedness, and compactness. So we've talked about continuity, what it means for a function to be continuous. Connectedness and compactness are what I want to talk about more or less for the rest of the semester, although there may be some other stuff in there. But anyway, connectedness is what the next chapter is about. Connected. Connected sets. A set can be connected or it can be disconnected. That's the opposite of connected. Connected sets is a very ordinary, sort of natural idea that I think anybody would come up with the idea, although it's not totally obvious how to make the proper definition. But the concept is pretty obvious, I think. Like, for instance, in R2, something like that is connected. This is connected. Something like this in 2 pieces. This is not connected because it's in 2 pieces. All right? That is not connected because it's in 2 pieces. How exactly do you make this definition, though? That's the trick, because when you make a definition, you want to say like X is a connected set means you can't really say like, well, it's all in 1 piece, because you have to explain exactly what you mean by piece. If there's 2 pieces, you have to say what you mean by 2 pieces, and that's not clear what you mean, really. Those are examples in R2. If I wanted to say examples like in R1, actually this is something that you talked about in your real analysis class, although I don't know if you remember. R, like all of R, is connected because it's all, in 1 piece. R is connected, but something like R with 1 point missing, R minus 0, this is disconnected. Disconnected means not connected, because it has kind of a part on the right side and a separate part on the left side, and they are separated by that missing point in the middle. They're in 2 pieces. Something like very simple, an individual interval. This is connected, but sort of like 2 intervals that are, separated by a little bit. This would be, maybe something like 1, 2, union, 2, 3. No, I meant 3, 4. 1, 2, union, 2, 3 is actually not separate, but this one is disconnected because it's got 2 pieces, right? Everybody got the idea? I think you probably had the idea just when I said that we're connected. It's a very ordinary concept, although the concept or the task of writing a real definition is not so obvious. And this, does anybody happen to remember the definition from real analysis? This is something that we talk about in the real analysis class, what it means for a set in R to be connected. I don't necessarily expect anybody to remember. It is defined in terms of, so first of all, it's easier to say what disconnected means than it is to say what connected means. And disconnected is defined in terms of what we call separations of the set. That is, disconnected means you can sort of break it into 2 pieces, 2 or more pieces. Although this can be a little bit confusing, but let me just say disconnected is easier to define, and then the definition of connected is just it is not disconnected. That's the definition of what it means for a set to be connected. Disconnected is easier to define. It means basically that you can separate the set into 2 different pieces, and what those pieces have to have some properties. So disconnected means there is a separation into two pieces. Actually, the pieces are typically called components, which is a separation is just a way of writing the entire space as a union of two things. Now, those two things need to have some special properties in order to count as a separation. Basically, it's X is, U union V. It's a union of two parts, two pieces. Now, it could be more than two pieces, but each of the U and the V are not required to be connected themselves. So, like, U might further break down into more pieces. Anyway, basically, a separation is a separation of X into two pieces, U and V, where in order to count as a separation, it has to have various properties. I thought maybe could we maybe brainstorm this together? I've been thinking about, I don't know if you think about this, I'm thinking about how this course has gone. This is the first time I've taught this course. One thing that I have thought is I would like to have involved you all more from day to day. I feel like a lot of times I'm just sort of talking, and I don't really like doing that all the time. So can we brainstorm maybe? I will try to let you guys maybe contribute. It's basically, X is written as a union of two things. I mean, the picture you should have in mind is like if X actually is in two separate pieces, and the two things are those two pieces, right? So this is the picture that you should have in your mind, where apparently that part is the U and that part is the V. This is the idea. A disconnected set has two pieces, or maybe more than two pieces, it doesn't matter, where there are important properties of the two pieces. Can anybody say what is important about those two sets, writing X as in two separate pieces? Yeah? Yeah, they have to be disjoint. That is, I would say, fundamentally the most important thing that makes it into a separation. It's that those two pieces don't overlap with one another. So first of all, I will say U and V are disjoint. That is to say, U intersect V is not empty, right? That's what the word disjoint means. All right, this is the main property. There are other sort of technical things that must be true. One hint, perhaps, is is empty. Yes, thank you for that. Is empty. U intersect V is empty. Sorry about that. That's what disjoint means. It is empty. Did you mean not empty or is empty? Is empty. You must have meant is empty. Yeah, to say they're not empty is the opposite of what I mean. They are not supposed to overlap at all right? There are a few more technicality properties. So this is the main one that I hope that somebody would immediately say during our little brainstorming session. I feel like we've had a great session so far of brainstorming. I'll give you a hint for the next property, is that the sets U and V are not allowed to be too stupid. There's sort of one stupid thing that you could always choose for U or V, which we want to disallow. Anybody have an idea for that? Yeah?
Empty set in R.
Yeah, they're not allowed to be the empty set, because then I would say, if you write X as U union V, but one of those is the empty set, then I would say that doesn't count as two separate pieces. That's just X is like the empty set union X. That doesn't count as two separate pieces for X. So they are not the empty set. Now he also said they're not the empty set, and they're also not everything. Now this condition here rules out them being everything, because if one or the other is everything, then their intersection will not be the empty set. So we don't have to say that specifically, but we do have to say U and V are non-empty. So, I mean, that's just U is not the empty set, V is not the empty set. All right, great. there's actually one more sort of technicality property, but actually this last one is very important. And I will try to demonstrate why this last property is necessary. If I consider, say, all of R, now R is connected. That means you cannot actually break R into two separate components. But check it out. How about this? I can write R as, say, something like minus infinity to 0, union, closed interval 0 to infinity. This is, this is a true fact, first of all, what I wrote. R really is the union of those two sets. I have things to the left of 0, and then things including 0 and everything to the right of 0. All right? So this really is an expression of x in two pieces. The problem, like this also doesn't really count as a separation. What this would look like is, the u and the v here. The u is this, and the v is this. This is not allowed as a separation. And it's kind of because the two sets, they're sort of like too close together or something. Like if you really allow one of them to omit a point and this one to fill that point in, then actually any set you can make a separation in this way by just taking some of the points, missing their boundaries, and then the other points including those boundaries that you missed from the first one. So this is not allowed as a separation. We want to disallow this kind of a thing because this is not really meaningful. And if you allow that kind of thing, then really any set can be separated, which we don't want any set to be separable. The way that we get around this is we also require U and V both to be open sets. That makes this kind of a thing not happen, right? The reason that this sort of thing happens is because this set omits a point, but that set fills in exactly that one point. That can't happen when both of U and V are open. So that's the last property which is required of a separation. U and V are both open. All right? And this is the definition of a separation. All right? It is, you write the set as a union of two things, and it has to have these properties. The two things have to be disjoint, that is, there's no intersection. They have to be non-empty, and they have to both be open sets. Maybe I'll just write that again. So this right here does not count as a separation of R. So here's the definition. I will say U and V are a separation of X when X equals U union V. U and V are non-empty, disjoint, open sets. That's what it means to be a separation. You can write the thing as a union of two non-empty, disjoint open sets. As he said, those sets also are not allowed to be all of X, but that ends up being a consequence of the fact that they're both non-empty. If one of them is all of X, then the other one would have to be empty, and that's not allowed. All right, so U and V are a separation of X when those things are true. And the definition of connected, so X is connected when there is no separation. Of X. All right. This can be a little tricky to demonstrate just because you have to somehow prove that no possible separation could possibly exist, but it's not so bad. X is connected when there is no separation of X. And we're going to say X is disconnected is the opposite of that. This is a little easier to work with. X is disconnected when there is a separation of X. All right. So I want to talk about a few specific examples. By the way, this is the same definition you use in real analysis. Although I don't know if you, well, apparently you don't remember, and that's fine. Like I said, it's typically easier to work with disconnectedness than connectedness. And if I just give you a set and I say, is it connected or disconnected, it's usually going to be easier if you're going to show it's disconnected. All you have to do is demonstrate for me what the separation is. If you want to show something is connected, you have to somehow argue that there's no possible separation, which is more complicated. Anyway, let's just look at some examples of disconnected. How about r minus 0? I mentioned this before. This is disconnected. Anybody want to tell me a separation? You have to give me two open sets which are non-empty, disjoint, and they cover up the whole space. This is what the set looks like, right? A separation is... Anybody got an idea? Yeah. Yeah, open intervals, minus infinity to 0 and 0 to infinity. Yeah, those are two open sets. They do, when you take their union, you get the whole thing. So one is like the one on the left and the other is the one on the right? This is the U, this is the V. When you take their union, you get all of r minus 0. They are disjoint. They are open. Is that everything? They are non-empty. Yeah, that's everything. All right, so this is a separation. So that means it's disconnected. This is how you demonstrate that something is disconnected. How about here's another example of something that I said before was disconnected. So this one looks like that and also that together, right? Anybody else want to suggest a separation here? This also is disconnected. I suppose what I'm talking about is this thing using the subspace topology from R. That's the only sensible way to interpret this as a topological space. Can anybody tell me what a separation shall be? You have to make two open sets that break this into two pieces. I think the two pieces are fairly obvious. Yeah. As open intervals. Okay, this is a good idea, although not quite right. Anybody feel like this is not quite right? There's something that's not quite. I mean, I like that they're open sets. The natural question is, why didn't you use the closed intervals? The answer is because I want them to be open sets. They have to be open sets. There's a problem with using these open intervals, though. Anybody have an idea? I don't mean to pile on our friend here. Yeah?
Like the endpoints, like 1 and 2 are not.
Yeah, we actually, if you just take these and take their union, they would miss some of these points which are in the original set. Remember, you have to write the entire set here has to be covered up by those two, right? It's supposed to be that x equals the union, U union V, but actually x is slightly bigger than that. So what can be done here? Any other ideas? Yeah?
Isn't it the same as x? Because it is the subspace topology, so it's those open.
Mm-hmm. Yeah, this is a little bit of a trick. I don't know. This isn't really a trick question, but actually, you should use this. Now, I already said, why don't you use the closed intervals? It's because they're supposed to be open sets, but those things are actually open sets using the subspace topology. That's the trick here. So these U and V, these are open in the subspace topology. Remember what that means is, I will say, since U is, the subspace topology means it's open if it equals an open set intersected with X. Can someone give me an actual open set, an open interval from R, which gives you U when you intersect it with X? U actually equals, this is what I want to write here. Do you have an idea? You mentioned the subspace thing to begin with. Anybody else? You want like some open interval here, which when you take the intersection gives you that.
0, 3.
0 to 3, yeah, I like that. Oops. Really, you need sort of any open interval that's just slightly bigger than that, right? Now, he went 0 to 3, which still works. That's quite a bit bigger, but as long as it doesn't grab any of the points from the other part, all right? So since U is this, that means U is open in the subspace topology, all right? So U is open in the subspace topology. This is a little strange because they look like closed intervals, but actually they are open in the subspace topology. A little something to think about. They're also closed in the subspace topology because they really are closed in the original set. So these things, the U and the V, are actually Clopen, if you will. They are closed and open when you consider them using the subspace topology. All right. That actually is something that connectedness actually has a lot to do with sets which are closed and open, which we'll come back to that in a little bit. I just had 2 more examples, and then we'll talk about Clopens. How about, these are a little more interesting, maybe, a little weirder. How about R, the lower limit topology? This, of course, looks like a line, but the lower limit topology, meaning open sets, have this form. That's what a typical open set looks like. All right. Is R with the lower limit topology connected or disconnected? Now, when I look at it, it looks like one contiguous thing. So my gut instinct would be, yeah, that's connected. But actually, if you follow through the definitions, this is disconnected. I will put exclamation because that's shocking. It is disconnected. Can you make RL into a union of 2 things, both of which are open sets in the lower limit topology? Actually, this should be reminiscent of a picture that I drew a few moments ago, like this here, right? Did I wrote this interval backwards. The lower limit should include the bottom one and not the top one. Sorry about that. It includes this limit point, but not the top one. All right. Actually, sorry to scroll, this example right here, we said this is not allowed because those 2 things are not open sets. But actually, in the lower limit topology, those 2 things really are open sets. And this really does make a separation of the line in the lower limit topology. So that is not allowed as a separation using ordinary, the standard topology on R, because that's not an open set. But actually, that is an open set if you're using the lower limit topology. So RL is disconnected. That's because I can do something like, here's a separation. RL equals, I'm just going to write exactly that one from that example up there. This union this. These are both open. All right, this is U and V. They're both open using the lower limit topology. So this is one sense. I don't know if you probably had this feeling all along, all semester long, but this is one sense in which the lower limit topology is really very weird. If you ask me what's so weird about the lower limit topology, I would say, topologically speaking, at a fundamental level, it's super weird because it's disconnected, even though it looks like a line. It's all sort of, I mean, it looks like one big connected line. But when you use this topology, it becomes disconnected. In fact, it's sort of extremely disconnected in the sense that here, using this separation, you can show that you can separate this set apart right at 0. So there's a 0 is somehow a point around which the set breaks apart. But actually, if you think about it, any real number could be used in place of 0. That means that this set actually can be separated anywhere. It doesn't have special points where there's like a boundary between one half and the other half. It's like every point is like that. You can separate the set wherever you like. It's very, very strange. Highly disconnected. All right, the lower limit. Okay, I got one more. And actually, there are a lot of similarities between these two examples. How about Q as a subset of R? Connected or disconnected? Q is like many, but not all, of the points on the real line. Not remotely all, actually. Connected or not? I would say this is disconnected. Does anybody have an idea how you could separate the Q out into two pieces? I would like for my answer to be somehow inspired by something like this, right? If you exclude 0 here, you can sort of, stick your fingers in the 0 and say there's these two parts. Can you do that with Q? Anybody have an idea? Yeah?
Negative infinity to pi, and then pi to...
Mm-hmm. Yeah, so I can say Q is a union of minus infinity to pi. Pi is not especially important. It just has to be irrational. Now, can you leave a little space here? Because actually I want to say something else. And then pi to infinity. Yeah, great. Yeah, this is the idea. Now, actually what I wrote there is not, well, this is not true, what I wrote. Anybody have a problem with what I wrote here? Q is equal to the interval minus infinity to pi union pi to infinity. Yeah?
Intersect Q.
Yeah, you have to do, this is a little technicality, intersect Q each time. So it's really that and also here, intersect Q. Yeah. So the two parts are all the rationals less than pi and all the rationals greater than pi. So this is the U and the V. All right. Are these open sets in the subspace topology? Yes, they are. Actually, we already wrote them like open sets in the subspace topology because they are an open set from R intersect with Q. So U and V are definitely open sets. They are also obviously not empty and they have no intersection. So this makes a valid separation. All right, great. Q also has the same property that I said about RL, which is that you can actually separate it at any point. Like I said, pi is not, there's nothing special about pi in this case. You can use any irrational number you like. And the irrationals exist sort of everywhere. You know, they're dense in the real numbers. So this also is a set which can be separated anywhere. All right, that's unlike, say, R minus 0. You have to separate it right at 0. That's the only place where you can break it up. Great. Let's discuss about Clopen sets and connectedness. Connectedness has a lot to do with Clopen sets. Connectedness and Clopen sets. All right. I'll try and draw a picture that gets to the connection, and then we'll write some details to check. But basically, if X is disconnected, this means it looks like, you know, basically two big pieces. And those pieces, in fact, they are the U and the V. This is how we typically think of, that's what a separation looks like. Half of the set, doesn't have to be exactly half or whatever, but you know, half of the set is U and the other half of the set is V. And U and V are each open. All right. What about closed? I would like to know, is U closed or is V closed or is something or other closed? U and V are each open. What about is U closed? To answer that question, you have to think about what is the complement of U, right? Remember, closed means that the complement is open. So when I'm asking, is U closed, what I'm really asking is, I will say, i.e. is X minus U open, right? Can we say, what is X minus U? If U and V are a separation of X, X minus U, the complement of U, is?
V.
It's V, yeah. If X is made up entirely of U and V, that's all of X, then the complement of U is V, and the complement of V is U, right? So when I say is X minus U open, the realization is that X minus U is V, and V is open, because that's part of what it means to be a separation. U and V are each open, all right? So I conclude U is also closed. All right? So when you have a separation, let me just summarize here. So if X equals U union V is a separation, then both U and V are actually Clopen, right? They are both open. That's part of the definition of a separation. But it is automatic that U and V are also closed, because the complement of U is V and the complement of V is U. All right? So if this is a separation, then both U and V are Clopen sets. And so this is another way of thinking about separations. You can think of a separation as being a union, X equals these two things, like we said. Or you could just think of a separation involves two Clopen sets. This is basically another way of phrasing it. So I want to write that as a theorem, which we've already kind of demonstrated half of, but it says X is disconnected if and only if there exists a Clopen set. Sorry if you think the word Clopen is stupid. I think it's a stupid word too, but it's convenient. There exists a Clopen set A subset X. Sorry, I should say A is a strict subset of X, a proper subset of X, with A not the empty set, and A is not X, just for emphasis there. Disconnected means you can separate it into two pieces, but it turns out those pieces are going to be Clopen. Actually, what I'm saying here is that it's disconnected is the same as really all you need is one Clopen set, because if A is one of the sets, then the complement of A is automatically the other set. That's where the other half comes. But if you want to talk about connectedness in terms of Clopen sets, really you only need to talk about one, which is a little, this can be convenient in some cases. All right, now I think we already demonstrated one direction of this. So if X is disconnected, that means you have this picture, and that means that U is Clopen. So this, what I said here, really constitutes a proof of the forwards direction here. So this way is, what I said above. Basically, if X equals U union V is a separation, then U is Clopen. And also V is Clopen. But anyway, what you would have to show for this direction is if it's disconnected, then there is a Clopen set where it's not empty and it's also not the whole thing. But we know that in a separation, this U is not the empty set and also is not the whole set. So that's one direction of the proof that's already done. What about the other way? We should discuss this, although it's not difficult. There exists a Clopen set, then you have to demonstrate that there is a separation somehow. So I'm going to say, let's assume a subset of X, is a, can I just write this in words? Proper, non-empty Clopen set, I should say subset. Proper subset means it's not equal to the whole thing, and it's also not empty, all right? Can we demonstrate, somehow use that to create a separation of X? So the picture here is X, and I will say what I want to show is that X is disconnected. All right, the picture would be X is some big thing, which actually we're going to show that X can be separated into two pieces, but we don't quite know that yet. And then we somehow have A as a Clopen subset. A is Clopen. I don't know how to indicate that on the picture. Maybe I will I will surround it with a solid line and also a dotted line to try and indicate that it is both a closed set and also an open set. All right. I want to show that X is disconnected. The way to do that is to say what is a separation of X. So for our separation, actually there's not much to say other than what it is. Separation. Use A equals, no, I have to say U and V, right? How are we going to choose U and V? All we have to work with is A, which is both closed and open. Would it work if we just use A for one of those two sets? That would be open. What could I choose for V then? I want V to also be an open set so that altogether it makes X, yeah?
X minus A.
Yeah, we can just use the complement here. So you take A and you also take everything else. Obviously those two things, when you take their union, it will be X because it's just one thing union together with the complement. So for our separation, we're going to use this. And so we should just check that all the various properties are true of this. So first of all, X equals U union V will be true. That's because this is just A union with its complement. Are U and V both open? U is assumed to be Clopen, so it's definitely open. So U is open. And also V is open. Can anybody say why is V open? V is X minus A. Yeah?
It's the complement of a closed.
Yeah, right. Because A is also closed. V is the complement of A. And so V is open. So V is open since it's the complement of a closed. All right. Great. What else did we have to? We have to also say that U and V are not empty, and that they have no intersection. So can we say the intersection is empty? That's because U and V are complements, so they definitely don't have any points in common, right? Since V is the complement of U. And then why are they both not empty? So U is not empty and V is not empty. That's because A is assumed to be a non-empty proper subset. So U is not empty, and also its complement is not empty because since A is a non-empty proper subset. All right. And I think those are all the properties necessary of a separation. I'll say Shun. All right. That means, so this is another way of thinking about connectedness, or more specifically, disconnected, right? A disconnected set has a proper non-empty Clopen subset. All right. So actually, you can say, for example, this is something that we've known for a long time. The lower limit topology, I mean, we just talked about this, but you could say, how do you know this is disconnected? I could say just very simply, since like this is Clopen, right? If it has a Clopen subset that's not the empty set and not the whole thing, then automatically it means it's disconnected. And we have already talked in the past about how those intervals in the lower limit topology are both closed and open. All right. How about this? What about some set? So any set or any space X with the discrete topology. Is this connected or disconnected? You could think of this in terms of Clopen sets. Are there any Clopen sets in the discrete topology? Remember, the discrete topology is one in which everything is open. Is it also true that everything is closed? It is, because closed means the complement is open. So if everything is open, then every complement of everything is closed, so everything is closed. So any space X with a discrete topology, all sets are Clopen. And so that means that it's disconnected, right? Disconnected just means it has some Clopen subset in it. That's not the whole thing. So all sets are Clopen, so it is disconnected. All right. The discrete topology on any space is disconnected. That is provided that it has more than one point. If it's just one point by itself with the discrete topology, then it's connected, because it can't be a proper non-empty. There's no proper non-empty subset at all. All right. Let's discuss. We got 9 minutes remaining. How about, can I say one more fun example? How about R, the finite complement topology? Remember that one? Is this one connected or disconnected? My initial feeling is this one's kind of crazy, so it's probably disconnected. My next feeling is maybe actually this is connected. Think about, can there be a Clopen subset here? Open means the complement is finite, right? What does closed mean? It means the complement of the complement is finite. That actually means the complement is infinite, right? The closed would be really sort of the opposite of this. You know, usually open is not the opposite of closed, but I think in this particular topology, open really kind of is the opposite of closed. The complement being finite. A closed set means it is the complement of a set whose complement is finite. That means that the complement is not finite, which is to say the complement is infinite. So open means the complement is finite. Closed means the complement is infinite. So can there be a Clopen set? I say no. No set can be both open and closed in here. And that means this space is connected because it has no Clopen, no proper Clopen subset, non-empty. All right, so open means the complement is finite. Closed means the complement is infinite. So there is no proper non-empty Clopen subset. So that means R, the finite complement topology, is connected. That also strikes me as weird, just because, I don't know. I have no real good way of thinking about R with the finite complement topology. To me, that's just totally weird on its surface. But apparently it's not completely weird because it's connected. All right. Great. Can I just maybe give us a little preview of what I want to talk about next time? This business about connectedness does all of these properties that we talk about certain types of sets or whatever. It is natural to consider how these properties are preserved or not by continuous functions. So big question, which we will answer next time. If I have some kind of, well, how about this? If x is connected and f going x to y is continuous, then is y connected? This is the basic idea that I would like to talk about. Can I just say the answer to that question is no, but kind of for stupid reasons. And there's an easy way to turn this into an actual theorem, something that's actually correct. So this question here, the answer is no, since x might miss some of y. I'll tell you what I mean by that. What I mean is, for example, you could have x being, let's say, the interval from 0 to 1, and then goes over using the identity function to y being the interval from 0 to 1 union the interval from 3 to 4. So here y is in two pieces, and if you send x over by a continuous function into one of those pieces, that's still a continuous function. Just because it's a continuous function here does not mean that y will automatically be connected, because I can just take this one piece and send it into this one piece, and y has this other piece which has nothing to do with anything. So the question here, if x is connected and I have a continuous function, that does not mean that y has to be connected. But it does mean that the range of f is connected. If I look only at the piece which this goes into, it has to go into one piece. It can't go into two separate pieces. This is a basic property of a continuous function. So I'll write this as a theorem. This is what we'll talk about next time. It says if x is connected and f is a function, is continuous, then the range, that is to say f of x, like that, the image of the domain, is connected. This is a true fact. This is something actually that you've seen in, I mean, even in a calculus class, this was probably brought to your attention at some point. Actually, I'm sure that it was. This is important in calculus. In calc. For example, we have 3 minutes. I can explain to you why this is important in calculus. So what I'm saying is, if I have, I'll just try and draw this as like the graph of a function. If the domain x is connected, let's say I have something like an interval, which in R, an interval is connected. If that's my x, then f of x, that is where the range is. Say if I have an actual continuous function here, then it has to look something like that if it's continuous. And then f of x is this, also connected, right? If x is connected and the function is continuous, then the f of x has to be connected. It's not possible, I will just say, you can't get something like x down here and somehow the range breaks up into two pieces. That's not possible for a continuous function. It can't do that, all right? There's actually a name for this. This is a famous theorem from calculus that says if your function is continuous, it cannot do that. Anybody know what I'm talking about? This, you have to think about it in a certain way to realize the connection. But basically, in calculus, what I'm saying here is if the range has this part and also this part, the range must include all the numbers in between, right? So the range in a single variable continuous function, the range must contain all values sort of in between, by which I mean these guys in the middle. There can't be like a missing part in the middle of the range. That's not allowed in calculus. Anybody know what I'm talking about here? There's a name that you all will recognize. It's about values which are in between. You might say, because we only have 1 minute left, you might say intermediate values. This is the intermediate value theorem. It says if you ever have two values in the range and another one in between, it has to also be a value of the function. So this is really, I mean, this theorem right here is basically the intermediate, some kind of super awesome version of the intermediate value theorem, which is not just about R, it's about any topological space. But this is the Rolls-Royce of intermediate value theorems. All right, so we'll talk about that next time. See you then.